Bismillahirrahmanirrahim. Bismillahirrahmanirrahim. Welcome back to the continual of chapter 3, part 2. Um, okay, we have a Shannon-Fano algorithm here. Okay, um, it is one of the earliest techniques developed for data compression, and it's provide a method to encode message by assigning a variable length binary codes to symbols based on their probability of occurrence. Okay, so there are 1, 2, 3, 4, 5 um, um, flows for a Shannon-Fano encoding. Okay, first is sorting by probability. Okay, we start with a list of symbols and uh, their relative frequencies of probabilities within the message. And these are sorted in descending order by probability. Okay. Next is to divide symbols. The sorted list is next split into two subgroups, attempting to make the total probabilities roughly equal in each group. Okay. For example, one subgroup is assigned to binary 1 and the other gets 1. Okay. Next is the recursive process. We repeat the division step on each subgroup by splitting further based on probability until every symbol has a unique binary code. And this will resulting in generating codes where higher probability symbols get shorter codes, while a lower probability symbols receive a longer codes. And the last one is the encoding, which involve replacing each symbol with its binary code sequence to compress the message. Okay. It is a simple to implement, but Shannon-Fano coding may not always produce the most optimal codes compared to more advanced technique. But because it's provided, not because, but it provided an early and straightforward way to incorporate symbol probabilities into cooperation. Okay, let's see the example 8. Okay, where we have the 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 types or 8 different colors with frequencies uh, different. Okay, different frequencies, each of them, right? Okay. First, as in the workflow previously, okay, we need to split the sorted code into two groups, okay, such as that cumulative probabilities are equal as possible. Okay, we have a 0 on the left and 1 on the right. Okay. So how to calculate is for example, we have 100 is code is 00 because it is in what stage or level 2, meaning that 2 bits. Okay. Okay. So we have 00 for black with 100 frequency, and that's why you see in the calculation 100 is refers to the frequencies times by 2 bit of code. Okay, for black. Plus 100 times 2 is equal, is refers to white, also with 2 bits. Okay, 0 and 1. Okay, And next we have a yellow with frequencies of 20, and we have 010 is refers to the 3 bits. Okay. Yellow is 3 bit because 010. Next we have B for blue, frequencies of 20 and times by 3 bits, 110. Okay, that is for 3 bits. Next we have the yellow with 20, orange, O for orange, okay, with 5 frequencies of 5 times by 4, because 4 is referring to 4 bits. And we also have a red, also 5, with the code of 1110. Okay, how you read the code is from a very first bit, daripada atas sekali, dia punya branch yang atas, you tengok yang paling bawah tu, frequency dia adalah 5. So untuk red, dia ada kod 1110. And then lastly is for purple and green with frequencies are 3 each of them. And then purple and green also got 4 bits. Okay, 4 bits. So that's why you multiply by 4. Okay, so in total you will have 584 bits. Okay. And what is next is to calculate the average. All right, the average by divide by 256. Okay, so 584 divided by 256 is equal to 2.28 bits per symbol. All right, and you also need to calculate the compression rate. Okay, which is 8 bit is the original bits, which is 8. Okay, 8 divide by 2.28 is equal to 3.521. Okay, so this is for the Shannon-Fano algorithm. So next we have the Huffman compression. Okay, as for the application, it's particularly in renowned formats like JPEGs, where it acts as a fundamental steps in the compression process, revolutionizing the storage and transmission of image data. Okay, and the Huffman compression was named after its creator, which is David A. Huffman. It is the technique which the ability is to minimize the average code length for symbol representation. And this technique has found its way into various applications. And today, we normally apply in JPEG. Okay, so as in JPEG, okay, um, the use of Huffman compression is like a fundamental step for JPEG compression process, and it contributes to the efficient storage and seamless transmission of image data, and still ensuring that our favorite photos and graphics are still preserved. Okay. And as for the short codes for frequent symbol, um, symbol normally occur frequently in the alphabet, uh, which assign a shorter length of code. Okay. So this approach optimize the representation of common symbols, leading to enhance the compression's efficiency. So it's like giving priority to the most frequently used words in a language, for example. Okay, and how the Huffman code what efficiently enhancing the compression is by translate to the shorter code for common symbol, which ultimately reduce the storage space needed and facilitate faster transmission for the compressed data. Okay, and so for the construction of Huffman tree, so imagine a binary tree taking shape, which constructed using a bottom up approach. Okay, so the symbols will be organized in descending order of probability, with a goal of creating an optimal structure of for code assignment. Okay, and we we also what as we transverse this Huffman tree, ascending from the bottom, nodes which represent symbols and branches define the path to each symbols. Okay, so symbol with the higher probability are positioned closer to the roots, ensuring a more efficient encoding scheme. Okay. Um, so for summary, Huffman compression, I think it's give the efficiency in the world of data compression. Okay, and this is the how we construct the Huffman tree. First is we know that it's popular data compression technique that use variable length codes to represent symbol based on their probabilities. Okay, so we'll discuss step by steps how is the process of constructing the Huffman codes. Okay, first is the initial sorting where we arrange a symbol in descending order, and then symbol with higher probabilities, as I said just now, will have a shorter codes, while symbol with lower probabilities will have a longer codes. Step number two, to pairing lowest probabilities. Okay, we pair the two symbol with the lowest probabilities and create a new combined symbol. Okay, this new symbol is the sum of the probabilities of the two symbol which being paired. Okay, number three is a resorting. After we paired lowest probabilities, we need to rearrange the symbol based on their update probabilities. Okay, which the symbol with higher probabilities will move up in the sorting order, while the symbol with a lower probabilities will move down. And we will repeat step number 2 and 3 until the sum of the probabilities of last two symbol is equal to 1. Okay, so this is to ensure that we have constructed a valid Huffman tree with a root symbol having a probability of 1. Okay, and binary tree generation next is when we constructed step number 1 until 4, our binary tree, Huffman binary tree is generated, and it is the representation of the hierarchical structure of the symbol codes. Okay, and the symbol are represent as their leaves, and the internal nodes represent the combined symbol. Lastly, the root of the binary tree, the last symbol in the construction process, will form the root of the Huffman binary tree. Okay, the probability of the root symbol is 1 indicate that it represents the entire set of the symbol. Okay, if the sum of the probabilities of the last two symbol is not equal to 1, it suggests the potential error in construction process, so that you need to redo the steps. Okay. Um, so what is next? Next is, yeah, okay, so these are the step 4 Huffman coding generation, starting from the initialization, repeat until one symbol is left, then you form the Huffman subtree, insert the node or insert the parent node, and then you may delete the children from the list. And lastly, we assign the code words. Either normally we assign 0 for the left branch and 1 for the right branch. Okay, so this is the example 9. Given a symbol with least relative probabilities of occurrence within a message, so first is to um, do the refer to previous slide where how is the construction code. Okay, first we have the initial sorting. Okay, you need to sort in the order of decreasing probability. So we have M1, M3, M4, M2, and M0. And next is to get two symbol with the lowest probability, which is M2 and M0. And this one is step number 2, which is pairing the lowest probabilities. Okay, and then you need to what to combine to form the A, which is 0.15 plus 0.1 is equal to 0.25. Okay, so now we will have the new list obtained as shown in this slide. Okay, um, now we can see that A is placed list number 2 next to M1 and M3. Okay, next is to repeat the previous step, which to sum up the pair of next to lowest probabilities. So we have M3 and M4 and combine as a B, which is equal to 0.39, which is placed in the very first of the list because it got higher probabilities. Now B is equal to 0.39. Okay. So we have M1 left because we know that we need to have the single you need to determine the root symbol, which is only okay, if the sum in the previous slide it said that the probability of the root symbol is 1. Okay, so kalau you tak dapat satu, maksudnya ada error lah dalam you punya step tu. Okay, so you need to combine B and C, yes, M1 and A, which will produce a C which 0.61. Okay, and then we have a new symbol which is D combine B and C is equal to 1. Okay, so lastly at step number 6, so we can see that the last one we have a D1. Okay, the root is D1. Okay, this is the step we have just now. A, B, C, and D. And finally, okay, we can rearrange the tree to a half-man tree shape, and then assign the 0 and 1 to each branches. So 0, 1, 0 is on your left and 1 is on your right. Okay. Um, and then we will have number 8, the resultant code words are formed by tracing the tree path from the root node to the code word leaf. Okay, start daripada root macam mana you nak baca dia punya code words dia. Okay, for example, we see M0. Okay, the M0 starting from the roots, we know that the probabilities or the frequencies we have 0.1. Okay, 0.10. So the code words start from the uh, root is 0, 1, and 1. Okay, next is M1, 0.36, and then the code word is 0 and 0. So for the M0, it's 3 bits. Okay, kita tengok ada 3 level. So it's mean that 3 bits. As for M1, it's only got 2 bits. Okay, which is 0 and 0. So seterusnya you boleh write the code words. Okay, as in the tables. Okay, lastly kita tengoklah M4. M4 from root we have 1, 1. So that's why M4 got code words as 1, 1. Okay, so this is the Huffman coding. When you were given the probabilities. Okay, let's see the example number 10. Okay, you have been given the string of Duke Blue Devils, which is a name of, if I'm not mistaken, the rugby club, I think, in US. Okay. Okay, what we need to do is first we need to count the frequencies. Okay, frequency count for each characters. Okay, from the string we have 3 times of E. Okay, D got 2, U 2, L got 2, space. Okay, the frequency counts must include the space. K got 1, B1, V1, I1, and S1. Okay, next is to build the Huffman tree. Okay. Okay, we start with the note for each character, and make sure you list down or you arrange the character in the descending mode daripada yang besar ke paling kecil. Alright. Next is, okay, then we then pick the note with the smallest frequency and combine them together to form a new note. Okay, the 2 selected notes are removed from the set but replaced with the combined note, and this continues until we have only 1 note left in the set. Okay, so as for here we need to combine S and 1, and the combination of S and 1, we got 2. Okay, and then we combine B and V. Also, we got the frequencies is 2. All right, and next is because K is 1. So we need to remember we need to combine the minimum frequencies. That's why we add K and K to the I and S. Okay, that's why we got 3, 2, 2, 3, and then under the 3 branches we got the K and B and V. Okay. So you repeat the process or the steps until you got only 1 branches left. Okay. So for example here, okay, 3 tambah 2 sama dengan 5. So yang tinggal adalah 4 And then this 4 with D and U, you need to combine with the E. Okay, that's why you got 7. Okay, you combine the frequencies. Okay, so now we got 5 and 4 is equal to 9 and 7. We with the branches of 3 and 4. Okay, and lastly, you need to combine the 9 and 7 is equal to 16. Okay, so you now have the root of 16 and then the branches each of right and left. Okay. Okay, now you can assign the codes to the tree by placing a 0 on every left branch and 1 on every right branch. Okay, so yeah, this one. Okay, so you have 0 on your right and 1 on your left. So how can you assign the code words as in the table? Okay, first you see the E. Okay, E we got the E starting from, you need to see from the root. So you got the code of 00. As for D, you will get 010. As for U, 011. And what is this? L is 100. And for space, SP is 101. Next is I. I is we are reaching 1, 2, 3, 4 bits. Okay, I is equal to 1100. That's why you got 4 bits. And as for S, you got 1101. K is 1110. And as for B and V, we are reaching the 5th bits. That's why you got 11110 for B and 111111 for the V. Okay, so what is next? Okay, so you dah ada dia punya code words. Okay, these codes are then used to encode the string. Okay, remember we got the Duke Blue Devils string. Now it's turned into 010, 001, and blah blah blah. Okay. This is refers to D is replaced by the code of 010. Okay, yang ni you refer balik you punya table tadi. And U is refers by 011. K is 1110 and so on. Okay, and we need to encode the entire string using the Huffman codes, and then we will get the following encoded sequences in 8-bit, starting from 010, sorry, 010, 00, 1111. Okay. Um, why we encode into 8-bit? Because it's to facilitate the storage and transmission. And normally we often group into bytes, which is 1 byte consists of 8 bits. So that's why the previous you need to combine 8 by 8. So we got 010, 0111111 and so on. Okay, so these 8 bits uh, okay, last for the last group 1101 XXXX. Okay, it doesn't fill the entire byte, so the X is represent the unspecified bits. Okay, these bits maybe reserved for the future use, depend on your implementation. Okay. So we can see if we compare the encoded sequence to the original string, we can see that it takes 7 bytes of space. In contrast, the uncompressed string consists of 16 characters, which will require 16 bytes. So, using the Huffman code, you can reduce the storage space required to represent the information. So, from 16 bytes to 7 bytes using the Huffman codes. All right, so as for the exercise, you have um, mm, the words hello. Okay. You need to what you need to do? Okay, use the Shannon-Fano algorithm and Huffman code um to 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 implement. Okay, so perform Shannon and Huffman code for the word hello. Okay, so for the Shannon Fano, remember we need to sort the symbol by the frequencies. Okay, so H is 1, E is 1, L is 2, and O is 2. Okay, and for the um, 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 for the Huffman, you need to divide the symbol into two equal group. Okay, so group 1, for example, you got HENO, and group 2 is L. So next is assigning codes, and lepas you assign code, you need to build the tree. Okay. Um, yeah, try to do this exercise using both Shannon-Fano and Huffman code algorithm, right? Okay, next is um, the lossy compression. Sorry, yes, lossy compression. We know that the lossless compression algorithm did not deliver compression ratio that are high enough. Okay, so hence most multimedia compression algorithms are lossy. So what is the lossy compression? The compressed data is not same as the original data, but a close approximation of it. Okay, and it yield higher compression ratio than that of the lossless compression. Okay, and the lossy compression normally used for compressed image and video files, but uh, the compression, the effect of compression still cannot distinguish by our eye visibly. Okay, but and that's why the lossy compression is acceptable, and these methods are cheaper, less time and space. Okay, and we have several methods in this lossy compression. We have JPEG, MPEG, and MP3. Let's see one by one. We have a JPEG compression. JPEG encoding. Okay. J is for joint, P is photographic, E is expert, and G is group. Okay. Basically, it's a name of group. Uh, and it's common to use compress. Okay. In this JPEG. Okay. How it's work? Okay, for example, first you have a grayscale image, and we need to divide a block into 8 by 8 pixels to limit the number of calculation. Okay, and what is the idea of the JPEG encoding is first to transform the 2D pixel group into a linear set of numbers that expose the redundancies present in the image data. And this is done by using the DCT, okay, which is the discrete cosine transform. And then uh, it will what the redundancies reveal are then removed using lossless compression techniques like RLE and Huffman coding. Okay, so the we divide the blocks into small 8 times 8 blocks, which enable the efficient processing. Then the DCT transform exposes repetitive pattern that can be condensed. And we finally do the entropy encoding compressors, which compress the quantized DCT values losslessly. Okay, so this multiple step or multi-step process will allow JPEG to reduce image file size significantly with a very minimal perceptual loss in quality, and that's why it's very popular choice for compressing a photograph and web graphic. All right. So the key here is to use 8 times 8 blocks and the DCT conversion. Right, so let's see what is the JPEG encoding DCT. Um, so DCT is a discrete cosine transform. It is the technique used in image and video compression, where it takes a block of pixel value like 8 times 8 block of 64 pixel and transform into a set of frequency coefficient. Okay, for example, let's say we have a simple 8 times 8 block that fades from black on the left and white to the right. Okay, this block we can say that it's contain lots of redundancy. Okay, because the neighboring pixel is tend to be very similar to each other. Okay, we then apply the DCT, where the most of the pixel values will transform to a zero, or near zero coefficients. And the main information is concentrated in just the first few low frequencies coefficient. Okay. So we then transform it into set of frequencies coefficient. Let's say we call the pixel block as PXY, where X and Y range from 20 to 70. All right. And then this contain the actual pixel brightness value. And then we convert this into the T, M, and N. Okay. The basic function or the base of this uh, function used in the transform have a cosine shape, okay, with increasing frequencies as m and n increase. Okay. What is next? All right, so what after we perform the DCT and then get the coefficient table of T, okay, the next step is quantization. Okay, quantization helps reduce the number of bits needed to encode the T of M and N coefficients, and it's done by dividing each coefficient by quantization constant and rounding down to an integer. For example, you have a constant of 10, then TMN value of 1, 2, 3. Okay, so if you would like to quantize down uh, to so the value of 1 to 3 need to be quantized, okay, to 12, 1 and 2, so that you get the smaller coefficient down to 0. Okay. Mm, okay. After we quantize the coefficient, we have lots of zero, especially in the higher frequencies. We to take advantage of this, the coefficient table is read in zigzag pattern. Okay, this one is the zigzag pattern. It goes diagonally from low frequencies, top left coefficient to high frequencies, bottom right. This clusters the zero together since the high frequencies are mostly zero after quantization. Okay, and the repetition of zero can be compressed using the RLE. And JPEG use Huffman code, one of the lossless compression, to encode the run length of zeros. Okay. So by quantization and compression the zero, the image block can be significantly compressed from original pixel values. Okay, but this comes at a trade-off of some loss of quality in detail. All right. So what is next is we have MPEG. Kalau tadi JPEG is what we have JPEG is joint photographic. Okay, now we have MPEG, um, moving picture expert group. Okay, which is a popular standard for video compression and encoding. And as introduced before, video consists of sequence of image frames over the time. Okay, and MPEG encoders take both spatial and temporal redundancy to achieve high of compression. Okay. As for the spatial, spatially each frame is divided into blocks and transformed using DCT, like in the JPEG image. This concentrate the frame information into fewer coefficient. And temporarily, MPEG encodes only differences between frames called the inter-frame coding. And this will be significantly reduce the redundancies. Okay. And as for the spatial compression, it reduce or spatially, okay, in spatial compression, each frame contains redundant pixels and pattern. So encoders use JPEG to compress each frame individually. And for the temporally, consecutive frame have duplicate content. So we exploit this by only encoding the interframe differences, not full frames. Okay. For example, you have a static scene with a moving mouth. Most pixel remain unchanged between frames. Only the moving mouth pixels need to be encoded. Okay, and uh, by eliminating spatial and temporal redundancies, this video can be compressed with a minimal quality loss, and redundant pixel both within and between frames also can be reduced. Okay, as you see in the image, um, MPEG can be classifies the frame into three main types: the I, P, and B, where I frames are self-contained with a full DCT encoded image. P is frames encode only changes from the previous frame, and B frames encode differences between the previous I frame and future P frame. Okay, so the sequence of I, P, and B is designed to minimize the interframe redundancies. Okay, and so for the summary, the combination of DCT, like in JPEG, interframe coding, and motion compensation in MPEG can provide the high quality video at reasonable bit rates. Okay. Last, we have the audio compression. Okay, tadi kita ada gambar, JPEG, MPEG for the video. Now we have the audio. Okay. Audio signals like speech or music always have the redundancies that allow the compression. For example, for the speech, the goal is to compress a 64 kilobit per second digitized audio stream. And for music, the compression target the 1.411 megabit per second, which is the CD quality signal. Okay. And two main approach are used. The first one is predictive encoding, which predictive encode use or analyze the waveform to predict the future sample based on the previous one. And then the perceptual encode remove inaudible or irrelevant information that of course, our ear cannot perceive due to masking effect. Okay, and for the perceptual coding, the MP3 is common perceptual codec. Remember, codec is the device to encode or decode. And okay, so this is the example for predictive encoding. Oh, sorry, the slide is not moving. Okay. Uh, for the predictive encoding, it's compressed audio by encoding only the difference between the sample, not the full values. Okay. The standard like GSM, G.729 is used to predict to reach bit rates of 13 kilobit per second down to 5.3 kilobit per second. Okay. And for the perceptual encoding, like I said just now, it remove audio information that is inaudible due to the masking effect. And MP3 normally target a CD quality audio and need 1.411 megabit per second. Okay. And so by eliminates the content or the audio that human ear cannot perceive, MP3s can compress this to 1 to 8 kilobit per second or lower while still retain a good quality. Okay. So in summary, I think we can say that predictive encoding reduce the redundancy between the sample, while perceptual encoding remove an inaudible sound. Okay, and together these techniques enable the significant audio compression. Okay, so these are the example of compression algorithm and codec. Uh, use. Okay, we have JPEG, which use 8 DCT blocks to transform pixel values into frequency coefficient. We have AVC video codec that's combine intra-frame DCT transformation, and HEVC, which is more advanced than um, what HEVC is more advanced than HAVC lah. Okay. Um, Using larger transform size, better motion prediction, and normally it offers up to 2 times better compression. We also have MP3, which is the audio codec, AAC, also audio codec, and so on. And I think that's all from me for chapter 3. Thank you very much and see you next opportunities. Assalamualaikum warahmatullahi wabarakatuh and goodbye.